Welcome to all to We Learn Fundamental Concepts of Stress and Strain in Civil Engineering Part 4 session. Today we learn about numerical calculations, free body diagram and idealizations. Numerical work in engineering practice is most often performed by using handheld calculators and computers. It is important, however, that the answers to any problem be reported with justifiable accuracy using appropriate significant figures. In this section, we will discuss these topics together with some other important aspects involved in all engineering calculations. Dimensional homogeneity. The terms of any equation used to describe a physical process must be dimensionally homogeneous. That is, each term must be expressed in the same units. Provided this is the case, all the terms of an equation can then be combined if numerical values are substituted for the variables. Consider for example in the equation. In equation S equals Vt plus of At square, where in SI units S is the position in meters, T is time in seconds, V is velocity in meter per seconds, and A is acceleration in meter per second square. Regardless of how this equation is evaluated, it maintains its dimensional homogeneity. In the form stated, each of the three terms is expressed in meters. The terms are each expressed in units of meter equals meter per second multiplied by seconds plus half multiplied by meter per second square multiplied by s second square. Meter equals meter per second square multiplied by second square, second will be cancelled. Half multiplied by meter by second square multiplied by second square, that means meter by second square multiplied by second square, the second square will be cancelled. Finally we got only remaining meter. The solution of dimensionally homogeneous equations can be used as a partial check for algebraic manipulations of an equation. Significant figures. The number of significant figures contained in any number determines the accuracy of the number. For instance, the number 5225 contains 4 significant figures. However, if zeros occur at the end of a whole number, it may be unclear as to how many significant figures the number represents. For example, 23400 might have 3 significant figures, or 4 significant figures, or 5 significant figures. To avoid these ambiguities, we will use engineering notation to report a result. This requires that numbers be rounded off to the appropriate number of significant digits and then expressed in multiples of 10 raised to 3, 10 raised to 6, 10 raised to minus 9. For instance, if 23400 has 5 significant figures, it is written as 23.400 into 10 raised to 3, but if it has only 3 significant figures, it is written as 23.4 into 10 raised to 3. If zeros occur at the beginning of a number that is less than 1, then the zeros are not significant. For example, 0.00821 has 3 significant figures. Using engineering notations, this number is expressed as 8.21 into 10 raised to minus 3. Likewise, 0.000582 can be expressed as 0.582 into 10 raised to minus 3 or 582 into 10 raised to minus 6. Rounded off numbers. Rounding of a number is necessary so that the accuracy of the result will be the same as that of the problem data. As a general rule, any numerical figure ending in a number greater than 5 is rounded up and a number less than 5 is not rounded up. The rules for rounding of numbers are best illustrated by examples. Suppose the number 3.5587 is to be rounded off to 3 significant figures. Because the fourth digit 8 is greater than 5, the third number is rounded up to 3.56. Likewise, 0.5896 becomes 0.590. and 9.3866 becomes 9.39. If we round off 1.341 to three significant figures, because the fourth digit 1 is less than 5, then we get 1.34. Likewise, 0.3762 becomes 0.376 and 9.87 becomes 9.87. There is a special case for any number that ends in a 5. As a general rule, if the digit preceding the 5 is an even number, then this digit is not rounded up. If the digit preceding the 5 is an odd number, then it is rounded up. For example, 75.25 rounded off to three significant digits becomes 75.2. 0.1275 becomes 0.128 and 0.2555 becomes 0.256. Calculations. When a sequence of calculations is performed, it is best to store the intermediate results in the calculator. In other words, do not round off calculations until expressing the final result. This procedure maintains precision throughout the series of steps to the final solution. We will generally round off the answers to three significant figures, since most of the data in engineering calculations such as geometry and loads may be reliably measured to this accuracy. Free body diagram. A free body diagram consists of a diagrammatic representation of a single body or a subsystem of bodies, isolated from its surroundings, showing all the forces acting on it. In physics and engineering, a free body diagram or a force body diagram is a graphical illustration used to visualize the applied forces, moments, and resulting reactions on a body in a given condition. A series of free bodies and other diagrams may be necessary to solve complex problems. A free body diagram is not a scaled drawing, it is a diagram. The symbols used in a free body diagram depends upon how a body is modeled. Free body diagrams consist of a simplified version of a body, often a dot or a box. Forces shown as straight arrows pointing in the direction they act on the body. Moments are shown as curves with an arrowhead or a vector with two arrowheads pointing in the direction they act on the body. One or more reference coordinate systems. Idealizations. Models or idealizations are used in order to simplify application of the theory. Here we will consider important idealizations. Particle. A particle has a mass but a size that can be neglected. For example, printing machine and beam. The printing machine size will be neglected as only we consider a load or weight of printing machine. When a body is idealized as a particle, the principle of mechanics reduced to a rather simplified form, since the geometry of the body will not be involved in the analysis of the problem. Concentrated force. A concentrated force represents the effect of a loading, which is assumed to act at a point on a body. We can represent a load by a concentrated force provided the area over which the load is applied is very small compared to the overall size of the body. In civil engineering, we study only the bodies are considered to be deformed under elastic limit or condition. The behavior of solid objects subject to stresses and strains.